If we are what we eat, then our teeth should say something about us. And that's what Dr. Fred Grein is looking into. Dr. Grein is no dentist. He's an anthropologist who studies fossil teeth like this one to piece together the story of human evolution, a tale with many chapters still missing.
The fossil record itself is incomplete. We have a dearth of evidence, as it were, to fill in many of the gaps in our knowledge. And that it's therefore important that every scrap of evidence be analyzed to its fullest.
What's being analyzed here is the tooth surface of a species of early man, Australopithecus robustus. Etched into each tooth lies the answer, Grein believes, to a controversy over how closely humans are related to robustus. The players in this 2-million-year-old family feud are robustus, a species called Australopithecus africanus, and members of our own branch, such as Homo erectus. For years, anthropologists believed that Africanus was the last common ancestor of the robust line which became extinct and the line which led to modern humans. Was robustus a close relative of ours, whose massive teeth and skull evolved by eating a greater volume of the same food as Africanus? If so, why did robustus look so different from its presumed ancestor? Could he have been another species altogether, whose large teeth and body were the result of a completely different diet from Africanus?
We've got an Australopithecus specimen in there. Let's center the
To answer these questions, Dr. Grein compared teeth from robustus and Africanus fossils to see if they differed from each other. First, a scanning electron microscope magnified the tooth surface. A lifetime of chewing leaves distinct wear patterns, which can be broken into two categories: pits and scratches.
Okay, I'd like to see what the proportion of the total of this micrograph here is made up by these deep scratches that are coming up in red. So why don't we see if we can get a histogram of that?
Okay.
For each magnified surface, the number of pits and scratches was tallied.
Okay, how many scratches have you got within 10, 20 degrees of buccal lingual there, something?
Using a 2-by-2 table with counts of pits and scratches for both robustus and Africanus, a chi-square analysis compared the distribution of wear patterns. The robustus teeth have a higher incidence of pitting, while Africanus has a greater number of scratches. Next, to find out what differences in diet produce these patterns, a new set of analyses was run, this time comparing the samples to primates whose exact diets are known.
The chi-square analyses showed that the robustus patterns didn't differ significantly from the patterns shown by monkeys that eat palm nuts and are known for being able to crack these very hard nuts. Australopithecus pattern, on the other hand, was found to not differ significantly from monkeys that would eat softer objects.
The pitting on robustus teeth indicated they ate hard objects, such as bark or nuts, while the predominance of scratches on Africanus teeth meant their diet consisted of soft foods, such as fruit and leaves. With this finding, the human tree needed rearranging.
Robust Australopithecines were not just large variants of A. africanus, and therefore they were not just simply a phylogenetic offshoot that increased in size from A. africanus, but rather that there were fundamental differences between them. And it would fit quite handily with the evidence on phylogeny as suggested by the black skull that was recently found, that in fact the robust Australopithecines have a very ancient history, quite separate from the lineage that would have led to humans.
So members of our branch, such as Homo erectus, can no longer call robustus a close cousin. With this new knowledge, scientists redrew our family ancestry to change the place of robustus. Working with just a few scraps of evidence, these insights into diet have advanced our understanding of the roots of the human family.
A two-way table of data from the fossil teeth study lets us compare a single categorical variable, type of tooth wear, between two different populations, Africanus and robustus. Since this makes a 2-by-2 table, we could use a z-test for two proportions, but instead we'll use this example to learn our new chi-square method. We'll label the columns scratches and pits. The two rows are the two species, Africanus and robustus. Then we can enter the counts of pits and scratches. To see how the species differ, Let's convert the counts to percents for each species. In this case, the proportions show that Robustus had roughly equal numbers of pits and scratches, while Africanus had distinctly more scratches and fewer pits in its teeth. Looking at the percentages gives us a good overall feel for the data, but for the inference procedures we're about to learn, we need to work with the frequency counts. Now the question becomes whether the differences in wear patterns are significant. After all, we wouldn't expect the patterns for the two samples to be identical. The observed differences might simply be due to chance, so what we need here is a significance test to tell us the probability of getting our result from random variation alone. Our null hypothesis is that the tooth wear patterns of the two species are the same, implying that there were no differences in the diets. The alternative hypothesis says the patterns are different, and therefore the diets were not the same. The first step in doing inference for this two-way table is to figure out what our results would look like if the distribution of pits and scratches were the same in both populations. We do this by calculating the expected counts for each entry in the table. First, we write the sums of the values in each row at the right of the table. Then the entries in each column are added. Finally, the totals themselves are added and put in the bottom right corner. Notice that the sum of the row totals equals the sum of the column totals. Both are 728, the total number of observations made. Now we need to find the expected count, which is the result we'd expect if the null hypothesis were true. For each cell in the table, we multiply its row total by its column total and then divide by the table total. For example, the expected number of scratches in the teeth of Africanus is 290 times 415 over 728, which is about 165. The expected count of pits in the teeth of the same species is 290 times 313 over 728, which is about 125. Doing the math for the other two cells gives us a picture of what we would expect if there were no differences in the distribution of tooth wear between the two species. The expected counts themselves are not equal because there were fewer total pits and scratches in the teeth of Africanus. Notice that the row and column totals are the same for the expected counts as for the observed counts in the original table. This should always be true, and it's a good way to check your math. Now, if the observed counts are far from the expected counts, we'll suspect that something other than chance is at work and will declare the null hypothesis false. To do this comparison, we use the chi-square statistic, written like this, invented in 1900 by the statistician Karl Pearson. The chi-square statistic is refreshingly simple. For each cell, you subtract the expected count from the observed count, square the difference, and then divide by the expected count. Do this for all the cells in the table and add the results. The chi-square statistic measures how far the observed counts deviate from the expected counts. The smaller the number, the closer the fit of the data. A chi-square of 0 means the data exactly fit the predicted values. In the fossil teeth data, the observed count in the first cell was 200 and the expected count was 165.3. So we subtract the two, square the result, and divide by the expected count, giving us 7.3. Doing this for each cell and adding the results produces a chi-square value of 28.2. Remember that small values for the chi-square statistic mean there's a good fit between the real data and the model. From our experience with other test statistics, we can guess that 28.2 is a large value, meaning the real data vary quite a bit from our model. In other words, we've produced evidence that the null hypothesis is wrong. There appears to be a real difference in tooth wear patterns and diets between the two species. In this case, a chi-square as large as 28.2 would occur by chance less than one time in 1,000.